Is everybody here? All right, so let me share my screen. I'll give people a few more seconds to get in here before we get started. They're gonna have to get into the second wave. 5, 4, 3. All right. Okay, so let me see who's this. All right, so anybody else that gets into the waiting room, they're gonna have to wait for the second wave. All right. Oh, I want to disable that. Let me. All right. Actually, let me see if I can pull up our homework, because it looks like we're wrapping up chapter 2, and so we should be ready for exam 1. I think that happens next week, or I think it becomes available this weekend, and it's available for 7 days for full credit. It seems like it got hot all of a sudden, but I am just getting out of the shower. And today has been like a lot warmer than usual. Feel like I need to break out my fans. Okay, calculus, this one. And I'm just gonna go to manage. I'm pretty sure it's in week 6. Let me see. Yeah, this is due the 19th. So that's probably like next week sometime. So it looks like exam 1 is next week, all right? Week 6, yep, because it goes from week 5 to week 7. So today we're gonna work on section 2.6 to wrap up chapter 2. And then so exam 1 will be over chapters 1 and 2, right? Okay, so we'll probably take next week to review for that exam. Maybe we'll take like Monday to review chapter 1, and then Wednesday next week to review chapter 2. Let me pull up the details on the exam. All right, so come on. All right. It looks like it becomes available on the 19th, and then it's due 7 days later, and it just covers chapters 1 and 2. You get unlimited attempts, right? And it's similar. It's similar to the quizzes, the formats of the quizzes, right? So the way our quizzes are designed, the exam is just a longer version of that. And unlimited attempts. So when you finish your exam, if you want a higher score, you're welcome to take it again, and you can take it as many times as you like until you get whatever score you like. And then I think from going forward, all the assignments should. Let me check it now. Actually, can I edit? Just want to make sure. It should be. Yeah. So the late penalty is set to 5%, right? So again, I changed as many assignments as I could to 5% late penalty. Some of them they wouldn't allow me to do it because students had already begun or began or whatever. Okay, so as usual, if you have questions, feel free to unmute yourself to get my attention. I can't really think of anything else. So, and this is like a fairly short section, so we'll take time to go through the section, and then if we have extra time, we'll probably go through homework questions. Let me check you guys in Zoom one more time. Okay. Okay. Right. Sit you there. Yeah. Okay. I think you're ready to rock and roll. I need to get a more quiet table. The sound is like irking me. Every time I sit down to do work, I hear it's like distracting. Okay. So let's see. So this final section in chapter 2, again, chapter 2 is covering exponential and log functions. And so with section 2.6, we're going to take a look at the derivatives of an exponential base A and log base A functions. I think we've looked at the derivative base E of exponentials and natural log, the derivative of those. So now we're going to generalize a little bit further. A few objectives here: differentiate functions involving a to the power of x, and differentiate functions involving log base a of x. So the derivative with respect to x of a to the power of x. So now think about it. If this were e to the power of x, the derivative of e is itself, but then the only additional part is we tack on that natural log of a, right? If it were e, it would be the natural log of e, which is 1, so you wouldn't even notice it. So the only difference is so the derivative of an exponential is still itself, but then when the base is an e, we have to capture that by saying times the natural log of it. Okay, so that's the difference when we're taking the derivative of a generic exponential. Okay, so one more time, the derivative of a generic exponential is going to be itself times the natural log of a. Okay, all right. Hopefully I have some juice in this guy. Let me see. So then for a, nope. Let's see. So for a, the derivative of y with respect to x is going to be the natural log of 2 times 2 to the power of x. So then b should be the natural log of 1.4 times 1.4 to the power of x. And that's dy by dx. Also, with me overheating, I also just ate like some turkey spaghetti. It was really good, and I had like a some Mardi Gras wings from Publix. Man, the Publix wings are like crack. Those things are dangerous. Okay, this one. Let's give this one a go. Let me think. So then for C, if we're going to find f prime of x, let me see. Okay. So it should be itself times the natural log of, let me think about it. Okay. So I'm going to do it this way. It should just be itself, which is this, times the natural log of the base, which is this. And then we got to say times the derivative of the power, which is going to be this. So that wouldn't have a lot going on there. We can go with this. We can change this to the natural log of 9 times that guy, but something along these lines. Okay, let's see how do we do. So the first one, we got the natural log of 2 times 2x. Natural log of 2 times 2x is there. Natural log of 1.4 times 1.4 to the power of x. And then 2 times, yeah, this is exactly what we got. 2 times the natural log of 3 times 3, right? So we kind of had to apply the chain rule along with this derivative of a generic log, because we had to apply the chain rule here, and that's where this additional 2 came from. Okay. That's the quick check. I'll leave those as exercises for you. So now we want to explore, let me see the time. We want to explore the derivative of log base a of x. Okay. I think the derivative of natural log, the way I remember it, is du over u. So, I mean, essentially it is still du over u, but then you have to tack on that additional 1 over the natural log of a. Similar to the previous example, it's just in terms of for logs instead of exponentials. Okay. All right, let's give these a go. So for part A, dy by dx is the derivative of y with respect to x. So 1 over the natural log of 8 times 1 over x. I think that's good there. Working on B, dy by dx. So common log is if there's no number written, then it's base 10, right? So when we go to find this derivative, it should be 1 over the natural log of 10 times 1 over x. Okay. That's fine. And then C, so f prime, 1 over the natural log of 3 times, it's du over u, so that's going to be 2x over x squared plus 1. And I think that'll suffice like that. So again, what we're doing is 1 over the natural log of a times the derivative of log, like how we used to do it, or like how we're familiar with. And then with d, so then f prime. So it looks like we have to apply the product rule here, right? We have one thing times another. So product rule is first times the derivative of the second plus the second times the derivative of the first. So the first is this guy. The derivative of the second is going to be 1 over the natural log of 5 times 1 over x. So that's the first times the derivative of the second plus, and I'll just continue down here, plus the second, which is this guy, times the derivative of the first is this guy. We could factor out, I'm trying to think, we got a lot going on here. So the x's would cancel here, like this x turns this x into a 2, or x squared. We could factor out an x squared. I don't know how much that would help us. I'm just going to kind of piggyback off what the prepared notes have. I know we're close. I'm just not sure how they want us to finish it. Let me see. 1 over the natural log of 8 times 1 over x. Natural log of 10 times 1 over x. Okay, so we got those. See, 2x over the natural log of 3. Now they probably condensed it. 2x. Okay, we're good. Natural log of 3 times x squared plus 1. We got that one. Okay, they did not factor out the x squared. So x squared over the natural log of 5. Yep, we got the x squared over natural. I think we got it. Yeah, it looks the same. Okay. Okay. Let's just kind of keep going. And we're actually almost done with this section. That's how quick it was. So we'll work some of the homework. And if you guys have, like, if you want to work some other homework from other than the section, if you just bring it to my attention, we can work on it together. Let me see the time. I still got like at least a full minute. Are we officially done? Let me see. Yeah, we're done with this section. Wow, that was fast. The following rules apply when we differentiate. So I think I will, let me change the view to the seamless. And come on here, I'd like to add a page. And we'll work some of the homework questions. Okay. So I got a full minute. So I'm just trying to wait until 6:15. All right, so let's work some of the questions from 2.6. And again, if you want to work something from another section, if you just ask, I'll pull it up. So let's start with 2.6. Change the view. I didn't even realize that was going to go that fast, but that's how it goes sometimes. So section 2.6. Okay, we got 21 questions. I'll do it here, I guess. All right, so we'll start with question 19. Let's see. Okay, let me check on you gentlemen in Zoom. I think we got one couple. Okay. I'm gonna go ahead and mark everybody else as absent. It's a good amount of absent. That's unnerving. Okay, let me let this gentleman in and let's keep moving. Okay. So let's look at this one. I don't know that I can get it much bigger. Okay, we'll go with this. So this comes from section 2.6, question 41. Because it means general inquiry. The population of Nilam doubles in size every 3 years. In 1994, the population was 25,000. Find an exponential function of this form that models Nilam's population after T years. Initial, what is the capital T? Find an equivalent expression that models of this form. What's the capital T? Is that the doubling time? The population doubles in size 3 years, and this population this form. So we have our initial population, the time. Oh, it's just trying to generalize. I'm thinking that T is the doubling time. I'm just going to confirm it here. If I click on view an example, it'll give me those details. And that's because of that. That's one of the main reasons I use Pearson. P naught is the initial quantity. Let me see. Cool. Give about this initial quantity. Let's keep going. Is doubling. So, okay, so that's it. The N is 2. So what's the capital T? The fixed time. Oh, that's the every 8 years. Oh, okay. So N is 2, and then the capital T is like the doubling time. So it doubles every 8 years. Okay. So find an exponential function of this form that models the data. Okay, let's try to take it from there. Let me see. Okay, so our N is 2. It doubles in size every 3 years. So that means that capital T is 3. In 1994, the population was 25,000 after 2 years, right? So if we let 1994 be our starting time, that means P naught would be 25,000. I think we have everything. I was about to take notes, but I was like, I don't think we need to. So we're just going to plug in everything that we're given. Use this. So let's see, our P naught, again, if we let 1994 be year 0, then our starting population looks like it's 25,000 times our N. So if we're talking about doubling, I think it was a 2 to the power of T over capital T was 3 years. The fixed time, it doubles every 3 years. So we said over 3. I think that's it. Let's go with that. Okay. So again, I just wanted you to see that process though. Like, this is why I use Pearson. I do acknowledge that some of these questions are ridiculous. So that's also why I'm not saying that this one is ridiculous, but some of them are. But that's why I do unlimited attempts. You know, system assessment take your highest score. I do a minimal late penalty. I don't really expect you guys to like commit a lot of this to memory. I just want you to I want to expose you to this stuff and give you an opportunity to process it, right? But as long as you get your assignments in with satisfactory scores promptly, you'll be fine, right? So when we weren't sure, we kind of read through the view and example. It gave those missing details that we may have been missing. And so because of that feature of the view and example, that's why I vouch for Pearson, right? Hopefully you can see that by now. Finding the equivalent exponential model of this form. So we need to do some algebra to convert this. Let me think. We have our starting amount. Can we solve for t? When t is 0, what are we missing? The rate. We're trying to solve for r. Okay, when t is 0, we get 25. We got that. I'm trying to think. So if we set our model equal to that model and plug in what we have, we don't have t, we need r, the doubling time. We could probably use the half-life formula. All right, okay, so I'm trying not to look at the notes. It seems like the only thing we're missing, because we have this starting amount, we don't have the rate, but we do have the doubling time. So maybe we can use the half-life formula, right? So let's try using the half-life formula to generate the rate, and then we'll have our equivalent model, and then we can probably proceed. So I'm going to take the screenshot so I can take some notes. I'm so glad I'm doing calculus first. So while my mind is fresh, I'm not like exhausted trying to do this. I can like actually think. Okay, let's copy. Come on, copy. I'm assuming that we got it. And matter of fact, I can just drag this if it lets me. Yeah. Okay. And okay. So we're going to incorporate, we're going to use the half-life, or we're going to use that to kind of proceed. So for part B, right, because we already did A. For part B, let me see. So we're working with this P of T equals P naught E to the RT. And we're also using the half-life. The way I remember half-life is the half-life equals the natural log of 2 over your rate. Or I guess just to keep the context, we'll put it over R. Okay, let's see if this works. So now let me say it doubles. If we want doubling time, okay, so what we're trying to solve for is our half-life. I think there is an application here, but I'm missing something there. So let me kind of backtrack a little bit. It doubles in size every 3 years. Let me see if I can use that information. Okay, so for instance, another way, sometimes we'll do, we have this information, but I'm gonna leave it as P naught. We don't know the rate and we don't know time. Okay, so let's try this. Let's use the one that we have from the first one. So we had this P of T. P naught was the what, 25,000. N was, I think we were doubling, so N was 2. We didn't have lowercase t, but capital T was every 3 years, right? And then we want to find an equivalent form of this where we have P naught, which is this, E to the R. Oh, okay. I think we got it, right? We just needed to put them side by side. So look at it like this, right? We got the 25,000 times 2. Now, they both have the t, so we have to the power of a third times t. 25,000. Oh, it's not exact, so we do need to do a calculation. Okay, so let's do some algebra. We can divide both sides by 25,000. This will give us 2 to the power of t over 3 equals e to the power of rt. Okay. Let's take the natural log on both sides. Right? It's coming along. We just got to keep going. So take the natural log on both sides. Okay. That allows this to come out and this. Now on the left, we're going to have, let's write it as 1/3 times t times the natural log of 2. Okay. On the right, the natural log and the e cancel, and so all that's left is r times t. We probably should set it to 0. but I am tempted to just divide by t. Let me see, if I subtract and factor, I think dividing by t might be okay. Let me see. If I set it to 0 and factor, we're going to have t times all of that equals 0. So then either t equals 0 or this equals 0. Yeah, let me do this. I feel a little bit better about this other thing, because sometimes when you just divide the t, it messes things up. So I'm going to set it to 0. I'm just going to see something real quick. So if we set it to 0, we'll have this natural log of 2 minus r times t, okay, equals 0. We can factor out t. This will give us 1 over 3 times the natural log of 2 minus r equals 0. Then if we use a 0 factor property, that means either the first thing is 0 or the second thing is 0. So if we set the second thing to 0 and solve, 1 over 3 natural log of 2 minus r equal to 0. So then ultimately it looks like we get r equals 1/3 times the natural log of 2. Okay, so that looks like our rate. Okay, we're going to see if that works. So then our equation is going to take on the form. So P naught is 25,000 times E to the power of whatever. I'm just gonna reference it as star. So star times T. Okay, so I think if we let R be star, it should work. And we can test some points before we submit it, but in the interest of time, I think I might just go with it. 25 times E. Okay, so let me see. Let me go ahead and calculate R. Nope. Right here. I need a new tab. Yeah, that's exactly what I needed. New tab. This guy. Okay. Now again, the textbook may have done it a more straightforward way. This is just how it unfolded when I thought about it. You don't necessarily have to do it this way. I was just kind of flowing with it. Now I'm getting this for an R. That seems pretty high. Okay, so then let's go full screen. Right here. Nope. Here. Come on. Okay. So here we got 25,000. And the R that we got, let's cross our fingers. Did we lose it? We got 1/3. Times the natural log of 2. Come on. Oh, it's because I got it plugged in. I'm going to have to unplug it. It always like throws a tantrum if I have it plugged in. So we said 1/3. Hopefully this works. Times the natural log of 2. If it doesn't, we'll dig and get to the bottom of it. It says round to 4 decimal places, 23,231, right? Because the 4 we would round down. So 0.231. Let's see if that works. So you're doing this thing. 231. Okay. That was an adventure, all right? We'll recap it. Let's try to finish out this example, and then we'll do a recap. What is Neelam's yearly percentage growth rate? So was it 23.1%? Yeah, let's go 23.1. So that was just the R that we just found. And then the population in 2000, so that's what, 6 years later? So then we just take our formula that we found and let T be 6. Okay. So I'll put it here. I'll go to my Y equals. So we had 25,000 times E to the power of R was 0.231 times T, and I'm putting here as X. Okay. And then I want to evaluate this function when X is 6 years later. So when X is 6. So almost 100,000. So 99,971. Let's see. Initial population, double the population that many times. So 6 times. Oh, okay. The population doubles in size every 3 years. Okay, so it's been 6, so then it doubles twice. So what is that? 50, 100? I mean, that's essentially what we got. Okay, get it. 100. That's fine. Okay. Let me see. So for E, how fast was Nalam's population changing in 2004? So they want us to solve for R when it's been what? If it's 2004, so that's 10 years later. So we let T be 10, and then we got to solve for R. We might have to use that formula. Okay, because like, well, we have our rate. Let me see. What is the population in that year? So, okay, thinking about it, like, we might have to find the population in that year using the first formula and then plug in T equals 10 into the second formula. That way we can have one equation and one unknown, and then we should be able to solve. I tried to just like plug in T equals 10 into the second equation, but we didn't know the population in that year, so we have to use the first equation for that, right? So let's hop over here. All right. I'll do it first. The first one that we found, we had the 25,000. The N, since we were talking about doubling, that was a 2, and that was T over every 3 years, right? And then when we did our calculations, we got a form of 25,000 E to the power of, the rate was approximately 0.231 times T, okay? Okay. So my thought process is, okay, we use the first formula to find the population after 10 years. And then, because they're asking us for the rate, right? How fast is it changing in 2004? So then we have our population, we let T be 10, and then we solve for R. Let me get a copy of these guys. Of course. Let's see. Okay, I think I got it. So if I go like this, yeah, that's exactly what I want. And then we can go like this. Okay, nice. Okay. Paste. All right, so let's give it a go. Let's see if it works, and then if we get it wrong, we'll dig to get to the bottom. So then, the population after 10 years should be the 25,000 times 2 to the power of 10 over 3. Okay. So I'll call that box whatever that answer is. We're going to get a result there, because I don't want to generate a result and round. You know, I'm trying to keep it exact until the end. So, you know, I'm just going to reference it like that. So now we're trying to solve for R. So then in the second equation, we have 25,000 times E to the power of R times T. So it's been 10 years and we're trying to solve for R. And this equals this guy, that's 25,000. Are we being recursive? No. Times 2 to the power of 10 over 3. Okay. I was gonna reference to this box, but now we can divide both sides by 2,500, right? So this divided by 25,000, this divided by 25,000. So then on the left, we have e to the power of 10r. On the right, we have 2 to the power of 10 over 3. Now we can take the natural log on both sides. Okay. These cancel. This comes down. This comes down. So then on the left, we have 10r. On the right, we have 10 over 3 times the natural log of 2. Okay. So I'll divide both sides by, is that what we had before? That is what we had before. That's what I was worried about. So we need, there's some other piece of information that we're missing because that's being a little bit recursive. So we missed something there. Let me think about it. How fast was it changing in 2004? That's after 10 years. I think I'm going to use, I'm going to use the viewing example. So I'm seeing, because we're missing something there. View an example. Just go to the end. I think we got all of that. Percent growth. Let me see. Okay, right here. Oh, the derivative. I just completely ignored it. Okay. So the derivative, that's what we're missing. Let's try taking a derivative. So let's go back. Right here. So if we want R, if we want the rate of change of the percent growth, now I'm just trying to decide which one I want to use. I think I'm gonna use the one that we found. Let me use this one. So if we have P of T equals the 25, 1, 2, 3 times e to the 0.231 times t. So then if we find P prime of t, all right, the derivative of e is itself, e to the power of 2.31 t. Oh, you know what? They might want us to use the other one since we introduced the derivative of the generic. Maybe I'll find both and compare and contrast. So times the derivative of the power. So we got to say times the 0.231. Okay, I think that's okay. And then so the question is asking P prime of t, P prime after 10 years. Sorry. So then in our calculator, we will put this e to the 0.231 times 10, and then that times 0.231. Okay. So let's see if that works. That makes a little bit more sense. I don't know why I just forgot about the derivative. 25,000. I think I got an extra 0 in there. Times E. 0.231 times 10. Okay. And then times another 0.231. Okay. Okay. No, that can't be right. We're trying. What's the rate of change? Let me think about it. We missed something still. When we take the derivative, still something that I'm missing. We get this, right? Times the original. Maybe it's just a number. I might just be overthinking that. Sometimes I do that too. This much persons per year. It might just be the same rate that we found already. I really don't want to just put it, but I think that's what it is. Give you an example. Come on. Go back to the end. I think it's the number that we already found. Right here. No, so they're using that other one. Okay, that's fine. So if we use that one, okay, P prime. Okay, yeah, so we used the wrong one. Let's use the other one. We get something like that. Okay, P prime is this. So the rate of change is this. To find the rate of change in this, substitute the value of the appropriate value of T. 6,000. Okay, so I did have that notion. Okay, so we did choose the wrong one. Let's let T be 10, and I think we'll get I think that'll give us what we're looking for. Okay, so this is it right here. Got this guy, 25,000, 2 to the power of T over 3. So then when we take the derivative, okay, that derivative is going to be itself, 2 to the power of T over 3. Then we need to say what? Times the natural log of 2, and then times the derivative of the power, which is what? A third. Okay. So then we let T be 10. Then we can just use it. And we're anticipating something like thousands of people per year. Okay. Finally got to the bottom of it. A little bit bulky, but I think we got it. 25, 1, 2, 3. Let's see, times 2 to the power of 10 over 3. Okay. Times the natural log of 2. And then times a third. That's still, why does that seem weird? After 10 years, 58,000, that's not right. What am I missing? Because we got something similar for the other one as well. This one. Let me check that one more time. P prime of 10. 10 years. 2 to the power of a third, or 2 times a third. Natural log of 2. Let's see. What was this initial population? 30,000 is similar to ours. 8 years. Okay, so maybe the number's good, and maybe I'm just not being confident, right? Because theirs double in size every 8 years, and then the other conditions were similar. Ours doubles in size every 3 years. So maybe that's why the numbers are so different. People per year. Rate of change. Let me see. I think it's this one. I'm just going to try this result here. 58. I'm not confident in this at all. It just seems too large. Like I don't. The number doesn't seem right. But I'm gonna just go with it, and we'll get to the bottom of it. 58. Nope, not there. Because the steps look similar to. Oh, come on! Are you still doing the same? You want to let us work? No, you're not. Okay, I got it. Okay, if I go like this, I can see both of them. Okay, let's try the 58,220. How many decimal places to the nearest whole number? So 221. That doesn't seem right. So, and it is right. Yeah, I just wasn't confident in the number. So it just seems weird though, right? But again, the only thing that kind of like made me kind of go with it, because their example, it doubled every 8 years. So it took longer. So the rate of growth was a lot smaller than ours. Ours was doubling every 3 years, right? So it's growing faster. Our rate of growth was much faster than theirs, right? So that one was an adventure, right? And we had the right thing. It's just, I wanted to be, oftentimes the numbers should make sense before you put them in. And again, the only telltale sign for me was that their rate of growth for the example we were looking at was 8 years and ours was 3. So I was like, okay, our number could be larger because our rate of growth is much faster. Our doubling time is a lot shorter than yours. That was an adventure. Okay, I'm going to try another one. That was a good that was fun. That took a good amount of time, but that's okay. So let's try another one. Number 2. Okay. But again, I mean, that's why I'd use Pearson, so we can go back and forth with a view and example when we get stuck on things like that. All right, so we're taking a derivative here. The derivative of E is itself times the derivative of power. I think I'm gonna just take my notes here. So if we're gonna find f prime, the derivative of E is itself. So we're gonna have E to the power of x squared plus 9x, okay? E to the power of x squared plus 9x, and then times the derivative of the power. So I'll just say times the derivative of the power is going to be what? 2x plus 9. And this needs to be in parentheses so that, we're clear that each of those terms is being multiplied by E. Okay, I feel good about that. I don't see anything else that we can do. Okay. Let's do another one. Let's go to question 5. Yeah, I started us off with a really good one. I was like, damn, I really had to think. Let's see. The derivative of natural log, right? The derivative of natural log is du over u, and that's it, right? Because natural log is the one that we did initially, so we don't need that additional term. So the derivative of this guy is 5/2 times x to the power of 4. So let me see, 5/2 times x to the power of 4. So du over u. So then we would have x to the power of 5. Uh-oh, that's not right. X to the power of 5 over 2. If we take it a step further, if we flip and multiply, it looks like the 2's cancel. And on top, we have 5x to the 4. And on bottom, it looks like we have x to the power of 5. Oh, and then we can go a little further from there as well. Because we have 4 x's on top and 5 on bottom, so they'll cancel. A lot of those are going to cancel, and it'll leave us with 5 over x. Looks like it's the final result. Du over u. Yeah, let's go with this. I'm going to get rid of all that. Go with this. Okay. All right, let's do another one. Let's look at question 4. Did we do question 4 already? Right here. Okay. So we're taking a derivative. Looks like we're doing the product rule. So we're saying the first, which is this guy, times the derivative of the second. So that's du over u. That's going to be 5 over 5x, which boils down to 1 over x. But then if we divide by x, this really becomes the power of 3. If I need to write those details, I can. But, when we say the first times the derivative of the second, the derivative of the second is going to become 5 over 5x. So the 5's cancel, and we're left with 1 over x. So then if we have x to the 4 divided by x, it gives us this. All right. So the first times the derivative of the second plus the second, I'm just going to put it in parentheses. Second times the derivative of the first, which is going to be 4x to the power of 3. We could factor out the x to the power of 3, but it doesn't change anything. Nothing cancels or anything of that nature. So we're going to go with this. Okay. Let's keep going. Generate. Let's look at question number 11. Okay. Okay, so this is like one that we introduced today, where we're taking the derivative of a generic exponential, so that we're going to have that extra term in there, right? So the derivative of an exponential is itself 3 to the power of x to the power of 4 plus 6, okay, times what? The natural log of 3 times the derivative of the power, which is going to be 4x cubed. Okay. All right, I think those are all the components. All right. So yeah, once we got past that number 19, like then we were able to, the rest of them were just flowing. I think it was 12. So I just go to the next question. Find the derivative, okay. So a derivative of an exponential is itself, okay. Come on. Okay. So then we get this 880 parentheses 1.678 to the power of t times, okay, we got this, what, natural log of 1.678, and then times, that's it, right? Because the derivative of the power is just going to be 1. I think that's it. Generate. Let's look at question 2. We did 2 already, so let's do 3. So the derivative of natural log is du over u. So that's going to be 7 over 7x, which is just 1 over x. Okay. We did 19, so let's see what's after 19. So let's do 20. Okay. In 2012, 34.1% of all glass containers were recycled. A beverage company uses 150,000 pounds of glass containers per year. After recycling, the amount of glass it pumps per year is still in use after 2 years is given by this. Okay. Find N of 4. So that one is just saying we're just plugging in let T be 4. We get a result. B is asking us to find N prime of 4 and explain its meaning. So we're taking a derivative. After recycling, the amount of glass in pounds still in use after 2 years is given by this. So then that's the rate of change of the amount of glass still in use after 2 years or at 2 years. Okay. When will 3% of the original amount of glass still be in use? We're solving for T. Are those percentages? Okay. So let's do this. My calculator's in there. Is it going? So there. All right. So what I'm gonna do? Go to my y equals, and I'm gonna put this function that was given. So we have this 150,000. 1, 2, 3. Parentheses. 0.278. Okay. To the power of t. So we're just gonna call it to the power of x. Okay. So then the first question asks us to evaluate that when x over t is 4. Okay. 2 decimal places. So 895.92. So then after 4 years, the amount of glass still in use is, right? In pounds. In the 4 pounds, right? This one. Okay. So then the next one, basically we take the derivative and then evaluate the derivative when t is 4. Okay. So I think I can take some notes here and get away with it. Let me suppress this. Come on. You're still doing this thing. Okay. Maybe if I go like this, that'll help it. Nope, it made it worse. All right. So I might have to zoom out. Okay. I think it's going to work. Okay, so the derivative, right? So the derivative of an exponential is itself, right? So that's going to be 150, 123, times this point, let's do 0.278 to the power of t, okay? Let me see, then we need to say what, times the natural log of 0.278, 0.278, okay? And then there's nothing in the power, so that would be that. Then we want to evaluate this when t is 4, right? So then our calculator, what we can do, you know what? I think the calculator can do it. I did it once before. Let me see if I can pull that up again. If I go to math, where was it? Derivative, in derivative. I think it was this guy. Okay. Function. So we want to say y1 of x when x is 4. There might be one more term that we need. Okay, so we got that when we put it there. Let me just manually do it and see if we get the same thing. So we get our 150,000, 1, 2, 3. Okay. Parentheses 0. Come on. 278. I'm going to say to the power of 4. Okay. Times the natural log of 0.278. Okay. Close out the log, close out the parentheses. We plugged in our 4 already. See if we get the same results. And we do. Wow. Wow. Right? So, you know, we had the function, we had the original function in our y equals, and we see in the above line, we were able to take the derivative, evaluate it when x is 4, right? So I think that in derivative is read, we're taking the nth derivative of our function y1 with regards to x, with respect to x, and we want to evaluate the derivative when x is 4, and we got the same result. We did it manually, and we did it with the function, so okay, so it says 2 decimal places. Looks like it's just 0.9. So a negative, let me see. Okay, so we got a negative 1146.9. So I'm gonna get rid of these notes. 1146.9. Negative 1146.9. Okay. So this means that after 4 years, the amount of glass still in use is changing. It's changing by, because we took a derivative, so it's a rate of change. It's changing by 1146.9 pounds per year. Pounds per year, right? In prime of 4 pounds per year. Yeah, that one. Okay. We get out of here in like 15 minutes. Let me look at one more. C. When will 3% of the original amount of glass still be in use? So they want us to solve for T. Okay. So it looks like we set the original equal to 3% and solve for T. Okay. If it's equal to 3, we divide by the 150, take the natural log. I should write it out. Do I have notes? Been a little bit lazy here. I'm trying to get you guys out of here. If it's equal to 3, if we divide by 150 first, so we'll say 3 divided by 150. Okay. And then we would take the natural log on both sides. I'm going to take the natural log of this guy. So divide. And then ultimately, T is going to be that result divided by the natural log of point, whatever. Divided by the natural log of 0.278. I think that's it. Okay. 3 decimal places. 851. So after almost 14 years. So 13.851 years. Okay, I just did it that way. Oh, let me see. 13.851, right? 3%. Do we need to convert this to a decimal? 278. Let me see. Natural log of 3, 150. That's a small number. Times natural log. Oh, I put times. I think it's supposed to be divided by. I think it's supposed to be divided by. I made a keystroke error. Right here, I think this is supposed to be divided by. 452, 8.452 years. Okay, let's see if that works. The amount of glass to the given percent, set the amount of glass to the given percent and solve for T using logs. Yeah. It's probably because we're trying to do it here. Let me check it one more time. So if we equal to 3, we divide both sides by 150,000. I got it there. Then we take the natural log. So we would have the log of this equals the log of that. So then ultimately T is going to be equal to, why isn't it working? 8.452. Oh, 2 decimal places. Man, following instructions, Jesus. Correct answer 2.74. All right, that one I got wrong. I don't even know why, but it's probably because I'm not writing it out. Let me think about it one more time. Divided by. Because I'm also kind of rushed, but we still got a solid like 10 minutes. So I'm gonna make use of my 10 minutes. Before I move away from this one, what I'm gonna do is, where is it? Cool. Maybe it's not there. Okay, let me click similar. We might need to do it. Okay, let's try it again. And it gave us instructions. I don't know why we got the wrong 2 point something. Okay, let's just try this one. Let's just try it again. Let's see. So we got this 25. 1, 2, 3. Come on. 0.444 to the power of x. Okay, we're good about that. Then we're going to evaluate this function. Come on. When x is 7. Around the 2 decimal places, so that would be 0.4, 850.4. Or we get this. After 7 years, external use is pounds. This one. Just get rid of this. Okay. So then we had a shortcut last time. What we did, we went to math, and I think it was number 8. So the nth derivative, we want to call on that function that we just put in. So the derivative of that with respect to x when x is, and we want to evaluate it when x is 7. So I'm just going to use this since we got it to work last time. 2 decimal places, negative 690.46. 690.46, okay. And then, so after 7 years, it's changing by pounds per year. So this one, the n prime is 7 pounds per year, okay. So now that last part, let's see if we can get to the bottom of this. I'll give myself maybe 4 minutes. I don't want to keep it past 7:10. 2% of the original amount of glass is still being used. Round to 2 decimal places. 2% of the original glass, and it doesn't look like we have the view an example. Let me see. 2% of the original glass was still being used after how many years? So we're solving for t. We set it equal to 2. Right there. We divide. So let me try writing it out. Maybe, but even I'm pretty sure I'm doing it right. Mm-hmm. After recycling. Mm-hmm. Mm-hmm. Okay. Let me try writing it out just to see if that makes a difference. It shouldn't, but it might. So let me write this out real quick. I just need this guy here. Okay. Let's copy real quick. And I'm watching the clock. I'm not going to keep you past, like, I'm not going to keep you more than 3 minutes. Let's paste here. You want to just be simple, right on the screen. I knew he was going to do that. You always do that. You always put it in some random place. Let me cut this. Oh, what is that? That's work. Okay, so I need to give a copy of this for you guys. Right here. Let's paste. All right. And let me crop it a little bit. Okay. All right. So it says we're solving for t, right? So we should be able to set this to, I think it said 2%. Wait a minute. B. Okay. Okay, wait a minute. I think we're set 2% of the original amount of glass. How many years? But that's not giving us a percent. Where's the percent? I want to see that little menu that they popped up, so I'm just going to force the wrong answer real quick. Set the amount of glass to the given percent of the initial amount, and then solve for t. Set the amount of glass to the given percent of the initial amount. Oh, okay. Okay, that's what I was kind of getting paused, right? Because the original function is not giving us in its percent, it's giving us a pound, right? So then the original amount was, I guess, the 250,000. So maybe we need to take 2% of 250,000, and then that's what our final pound is going to be, and then we'll get it, right? So I think that's what we were missing. Right here are pounds and not percent. So we needed the proper units, right? So if the original is 250,000, then what we're going to do, if we're solving for t, we're going to say the 250 1, 2, 3, 0.444 T, and we want 2%, so that's going to be 0.2 of the 250,000. Right, so I think what we were missing before was that last part there, right? I think that's what we were missing. So now when we divide, we'll get this, okay, equals this. Take the natural log, we'll get this, natural log of this, equals the natural log of this, and then divide, yep, this looks better. Natural log of this over the natural log of this. Okay, let's try this. I know I said this like a million times just now. I'm just trying to get you guys out of here. I could even recall the other one real quick. This right here. If it were 3%, those cancel. So I think if we just get rid of this guy here, we'll have our result that we were looking for from the previous. No, 0.03. So insert. Okay. 2 years. I think that was right. Okay. So let's try ours. Let's try the one that we're working on. So the natural log of 0.02 divided by, I hope this works. I'm trying to get you guys out of here. 0.444. I got to get ready for my next class. Okay. 4.82 years. 4.82 years. Here, cross our fingers. 4.82 years. Yeah, so that's what we're missing, right? So as a quick recap for that final part, for that part C, I think initially we just set it equal to 3, but that was a percent, but the original formula was giving us pounds, so the units weren't matching up. So that was the first red flag. So then the hint was we needed to set it to a percent of the original amount, right? So the original amount in this case was the 250,000. We wanted 2%, so we had the only change we needed to make was we needed to find 2% of the original, then proceed. That was the only thing we were missing. So we got to the bottom of that one. All right, gentlemen. So that was, I think those are really good questions, right? So again, like this, that's how it goes. Like, just ask. Like, again, I do acknowledge that some of these questions are a little bit ridiculous. That's why I do unlimited attempts. That's why I only do a nominal late penalty. You know, I try to encourage you guys to just ask and collaborate, you know, because like I can see where that would be intimidated, but just keep pushing, like keep pushing and keep going. So you see, even though I did some of these several times, it gave us credit for it, right? With the homework. You saw when I got it wrong, I just clicked similar exercise and I kind of kept pushing until I was able to get it right, right? So at least with the homework, you know, the homework is really just practice. It's there to get you ready for the exams. And even with the exams, that's more of like, it's a little bit closer to like endurance energy, because if you're somewhat savvy, you know, you can get a decent score. If you get it wrong, then obviously you got to go back, dig, do some research, and try to get a better score. And then obviously, if you keep trying, you'll run out of energy, right? You get tired. So the efficiency there comes from practicing leading up to it. All right. So we are officially ready for exam 1, covering chapters 1 and 2. I talked about when it was going to become available. Let me pull it up one more time before I let you guys go, so that you'll know. Right here, manage. So exam 1 becomes available, I think it was the 19th, right here. It's available on the 19th, and then it's due a week later, right? Whatever day of the week that is. Okay. That's probably at the start of class next week on Monday. Pull the calendar up. I think that's Monday, yeah. So the 19th is Monday. Okay. So on available on Monday at the start of class. Credit is due the following week. If you submit it past the due date, that's okay. The highest you can earn is a 95, which is still nothing to scoff at. Okay. Are there any burning questions before we go our separate ways? Share. Send this to box. Come on. Trying to get this gentleman out of here. Come on. Let me see. Spring traditional calculus notes updated daily. And I always forget to change that one. So we got a copy. So when this bar finishes loading, you'll receive a copy of anything that you saw me writing. And with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy your meeting, gentlemen. And we'll meet back Monday, same time, same place. Take care. Peace.
Take care.
Yep. All right, gentlemen. So I do need to kind of log out. Take care. I'll see you next time.